All right, so Friday, November the 13th, and we're going to continue with chapter 8. First, I want to show you a video about the Z-scores. We didn't go over that specifically, but I'm going to show you this video.
Here's the second problem from CK12.org's AP Statistics Flexbook. It's an open source a textbook essentially. I'm using it essentially to get some practice on some statistics problems. So here, number 2, the grades on a statistics midterm for a high school are normally distributed with a mean of 81 and a standard deviation of 6.3. All right. Calculate the Z-scores for each of the following exam grades. Draw and label a sketch for each example. We could probably do it all on the same example, but the first thing we'd have to do is just remember, what is a Z-score? What is a Z-score? A Z-score is literally just measuring how many standard deviations away. How many standard deviations away from the mean. From the mean.
Okay, I just want to stop there. Can anyone tell me why computing a Z-score or Z-score is beneficial for doing statistics or examining data? No one? Oh, I guess you're not reading the text. Okay, when you create a Z-score, what you are doing in effect is standardizing the data. What you're trying to do is reduce the skewness, if there's any, or to move the extremes closer to the middle, and those people in the middle, or the scores in the middle, or the data in the middle gets closer together, so it emulates a normal curve. When the data looks like a normal curve, it's easier to interpret. Okay, does anybody not understand that? That is what you are doing with a Z-score. All right, everybody's good? All right, we'll continue with the video.
From the mean, just like that. So we just have to calculate how many standard deviations each of these guys are from the mean, and that's their Z-scores. So let me do part A. So we have 65. So first we can just figure out how far is 65 from the mean. Let me just draw one chart here that we could use the entire time. So this is our distribution. See, we have a mean of 81. So we have a mean of 81. That's our mean. And then a standard deviation of 6.3. So our distribution, they're telling us that it's normally distributed. So I can draw a nice bell curve here. They're saying that it's normally distributed, so that's as good of a bell curve as I'm capable of drawing. This is the mean right there at 81. And the standard deviation is 6.3. So one standard deviation above and below is going to be 6.3 away from that mean. So if we go 6.3 in the positive direction, that value right there is going to be 87.3. If we go 6.3 in the negative direction, where does that get us? That's what, 74.7? 74.7, right? If we had 6, it'll get us to 80.7, and then 0.3 will get us to 81. So that's...
Okay, so I just want to show you, if you are unclear. So you have, I think that's a 65, okay? And you know what the standard deviation is, 6.3, okay? So what they're doing in the video is, if you look at these dotted lines, you have the mean of 81. One standard deviation to the right gives you 87.3. One standard deviation to the left gives you 74.7. Between these two dotted lines is one standard deviation. And what is the percentage under the curve? Does anybody remember what that is? You should know what this is. Think of what rule would you use to figure that out. No one? Okay, must be Friday. Everybody's sleeping. 68%. All right? So that's the easy way of looking at this and the easy way of using the Z-score. So I will continue.
One standard deviation below and above the mean, and then you'd add another 6.3 to go to 2 standard deviations, so on and so forth. So that's at least a drawing of the distribution itself. So let's figure out the z-scores for each of these scores. So 65 for each of these grades. 65 is how far? 65 is, it's maybe going to be here someplace. So we first want to say, well, how far is it just from our mean? From our mean. So the distance is, we just want a positive number here. Well, actually, you want a negative number because you want your z-score to be positive or negative. Negative would mean to the left of the mean, and positive would mean to the right of the mean. So we say 65 minus 81. So that's already how far away we are, but we want that in terms of standard deviations. So we divide that by the length or the magnitude of our standard deviation. So 65 minus 81, let's see, 81 minus 65 is what? It is 5 plus 11, it's 16. So this is going to be minus 16 over 6.3. Take our calculator out, and let's see if we have minus 16 divided by 6.3, you get minus 2. Looks like 54, approximately equal to minus 2.54. That's the z-score for a grade of 65. Pretty straightforward. Let's do a couple more. Let's do all of them. 83. So how far is away from the mean? Well, it's 83 minus 81. It's 2 grades above the mean. But we want in terms of standard deviations, how many standard deviations? So this was part A. A was right here. We were 2.5 standard deviations below the mean. So this was part A. 1, 2, and then 0.5. So this was A right there, 65. And then part B, 83. 83 is going to be right here, a little bit higher. We're right here. And the z-score here, 83 minus 81, divided by 6 will get us, let's see, here, the calculator. So we have, 83 minus 81 is 2, divided by 6.3, 0.32, roughly. So here we get 0.32. So 83 is 0.32 standard deviations above the mean. And so it'd be roughly one of the standard deviation along the way, right? Because this was one whole standard deviation. So we're 0.3 of a standard deviation above the mean. Choice number C, or not choice, part C, I guess I should call it. 93. Well, we do the same exercise. 93 is how much above the mean? Well, it's 93 minus 81 is 12. But we want it in terms of standard deviation. So 12 is how many standard deviations above the mean? So it's going to be almost 2. Let's take the calculator out. So if we get 12 divided by 6.3, it's 1.9 standard deviations. It's z-score. Its z-score is 1.9, which means it's 1.9 standard deviations above the mean. So the mean's 81. We go one whole standard deviation, and then 0.9 standard deviations, and that's where a score of 93 would lie right there. Z-score is 1.9. That all that means is 1.9 standard deviations above. Let's do the last one. Do it in magenta. D. Part D. Score of 100. The score of 100. We don't even need the problem anymore. A score of 100. Well, same thing. We figure out how far is 100 above the mean, where the mean was 81, and we divide that by the length or the size or the magnitude of our standard deviation. So 100 minus 81 is equal to 19 over 6.3. So it's going to be a little over 3 standard deviations. In the next problem, we'll see what does that imply in terms of the probability of that actually occurring. But if we just want to figure out the z-score, 19 divided by 6.3 is equal to 3.01. So it's very close, 3.02 really, if I were to round. So it's very close to 3.02 Its z-score is 3.02, or a grade of 100 is 3.02 standard deviations above the mean. So remember, this was the mean right here at 81. We go 1 standard deviation above the mean, 2 standard deviations above the mean. The 3rd standard deviation above the mean is right there. So we're sitting right there on our chart, a little bit above that. 3.02 standard deviations above the mean, that's where a score of 100 would be. And you can see the probability, the height of this, that's what the chart tells us. It's actually a very low probability. And actually, it's not just a very low probability of getting something higher than that, because we learned before in a probability density function, the probability, if this is a continuous, not a discrete, the probability of getting exactly that is 0 if this wasn't discrete. But since this is a scores on a test, we know that it's actually a discrete probability function. But the probability is low of getting higher than that. You can see where we sit in the bell curve. Well, anyway, hopefully this at least clarified how to solve for z-scores, which is pretty straightforward mathematically. And in the next video, we'll interpret z-scores.
Okay. So, are there any questions about that? Any questions about the z-score, finding the z-score, what the z-score means? No questions? Okay, great. All right. Okay, yes, we did this one, point estimates. Go to the next slide. Okay, population standard deviation is unknown, and we're going to look at the t distribution. So it's 2 different distributions, the z and the t. So let's just go over this. In most sampling situations, the population standard deviation, sigma, is not known. Below are some examples where it is unlikely the population standard deviations would be known. The dean of the business college wants to estimate the mean number of hours full-time students work at paying jobs each week. He selects a sample of 30 students, contacts each student, and asks them how many hours they worked. The dean of students wants to estimate the distance the typical commuter student travels to class. She selects a sample of 40 commuter students, contacts each, and determines the one-way distance from each student's home to the center of campus. The characteristics of the t distribution, it's like the z distribution, and it's a continuous distribution. It is like the z distribution, bell-shaped and symmetrical. There is not one t distribution, but rather a family of t distributions. All t distributions have a mean of 0, but their standard deviations differ according to the sample size. In the z distribution, it has a mean of 0, and can tell me what the standard deviation is for that? For the z distribution, always. I guess I better ask somebody. So Amir Hossein, what's the standard deviation for a z distribution? Amir? You can say you don't know. It's all right.
I'm sorry, what was the question? I didn't get that.
The question is, in a z distribution, the mean is 0, and what's the standard deviation?
It's I think it's area of 68.
Sorry, what is that?
It is in area of 68, right?
Or 68, but that is equivalent to what? What standard deviation is that equivalent to? 68%.
I don't know that.
Yeah, you do know that. It's 1.
Yeah, 1, right.
1, because the 68% represents the positive 1 standard deviation from the mean and the negative standard deviation from the mean. Okay, so this is important. In the z, the mean is always 0, and the standard deviation is always 1. In a t distribution, the mean is 0, but the standard deviations can differ. Okay?
Right, got it. Thank you.
Okay? All right, and the fourth item, the t-distribution is more spread out and flatter at the center than the standard normal distribution. As the sample size increases, however, the t-distribution approaches the standard normal distribution. Okay? Because the z distribution is as close to the normal distribution as possible, but the t-distribution is not, only when you increase the sample size. So that is the important factor there. All right, so I'm going to show this video on the t-distribution. Okay.
Let's take a quick look at an introduction to the student t-distribution, which you might also hear called student's t-distribution, or simply the t-distribution. This video goes into some of the mathematical details, such as how the t-distribution arises, its probability density function, and mean and variance. I have another video that provides an applied, non-technical introduction. The t-distribution is an important continuous probability distribution that is widely used in statistical inference. The t-distribution is very strongly related to the standard normal distribution. Let's look at that a little more closely. Suppose we let the random variable z have the standard normal distribution, and we let the random variable u have a chi-square distribution with nu degrees of freedom, and z and u are independent random variables. Then if we take the standard normal random variable z and divide by the square root of the chi-square random variable u divided by its degrees of freedom, we end up with a random variable that has the t-distribution with nu degrees of freedom. So we often represent this random variable with the capital letter T. Now this might all sound a little abstract, and you might wonder when we would ever wish to divide a standard normal random variable by the square root of an independent chi-square random variable over its degrees of freedom. But this actually has some common and important practical applications for us. If we are drawing n independent observations from a normally distributed population with mean mu and variance sigma squared, then the quantity x bar minus mu over s over the square root of n has the t-distribution with n minus 1 degrees of freedom. Here the sample mean x bar is a random variable representing the mean of the n observations, and the sample standard deviation s is a random variable representing the standard deviation of the n observations. This might not look like the quantity given on the previous slide, but it can be shown mathematically that this satisfies those conditions. That's something you might show in a mathematical statistics course. An implication of this is that the t-distribution often arises in statistical inference on means, and in other related scenarios, when we are sampling from a normally distributed population. This is a situation that comes up very frequently in statistics. In practice, we very often use the t-distribution in inference procedures. Here's the probability density function of the t-distribution with nu degrees of freedom. The PDF of the t-distribution is not something we work with directly very often. Gamma represents the gamma function, and I'll let you look that up if you need to learn about that. If a random variable has a t-distribution, then it...
I'll just stop it there. So this is not something you have to memorize. This is just explaining the t-distribution mathematically. So you really don't have to worry about it, just so you're assured about that.
Can take on any finite value. There is one parameter, nu, the degrees of freedom. In practice, this will typically be a positive whole number value, but it doesn't have to be an integer. We'll take a look at a few plots in a moment, but a few things to take note of now. The median of the t-distribution is 0. For the mean and variance, there are a couple of technical restrictions. The mean of the t-distribution, mu, is equal to 0 as long as the degrees of freedom nu is greater than 1. Otherwise, it's undefined. And the variance of the t-distribution is equal to nu over nu minus 2 as long as nu is greater than 2. A very important notion is that as the degrees of freedom increase, the t-distribution tends toward the standard normal distribution. Let's plot the PDF and see what it looks like. The curve in white is the standard normal distribution, and the curve in green is the t-distribution with 1 degree of freedom. I've truncated the plot here at -6 and 6, but the possible values do go off toward positive infinity and minus infinity. Like the standard normal distribution, the t-distribution is symmetric about 0, but the t-distribution has heavier tails, meaning more area in the tails, and it has a lower peak. As the degrees of freedom increase, the t-distribution tends toward the standard normal distribution. I'm going to let the degrees of freedom increase from 1 through 20, and we'll see what happens. Here the curve in green is the t-distribution with 20 degrees of freedom. I'm stopping at 20, but we'd see that if we continue to let the degrees of freedom increase, the green curve would get closer and closer to the white normal curve. The median is right here at 0, and the mean is also 0. The variance is the degrees of freedom over the degrees of freedom minus 2. In this case, that's 20 over 18. Note that's a little bigger than 1, which is the variance of the standard normal distribution. Even though these two curves look very similar here, there are some important practical differences. The t-distribution with 20 degrees of freedom still has quite a bit more area in the tails. And very often in practical problems, we are interested in the area in the tails. So there are important differences between the t and standard normal distributions, even if they look similar when plotted. In practice, we often want to find areas and percentiles of the t-distribution, and that requires integrating the probability density function. Unfortunately, there is no closed-form solution, and that integration must be carried out numerically. Fortunately, that's been done for us using computer software, and we will find areas and percentiles for the t-distribution using software or a t-table.
Okay, so you do have on the website and in the text, you do have a t-table. You can look at that. It's similar to the Z table, but I'll carry on and let them just finish here. And that's it. Okay. So I just want to explain that if people have heard of a t-score, basically what you're doing is you're doing a preliminary investigation of the data. And if you get a t-score, unless you have a large sample size, which is going to give you a large degrees of freedom, your t-score is not as strict as the z-score, because the z-score is adjusting the data. The t-score is looking at the raw data. So having usually about 30 degrees of freedom, or 32 sample size, or whatever the sample size is going to be over 30, that's going to give you a close approximation. But the t-score is usually referred to as a liberal score, which means it may take data in and give you a false positive, and you believe that your data is statistically significant. If you get that and you're using a t-score, my recommendation is converting it to a z-score, of course, if you have a sample size that's large enough, usually over 30. So is there any questions about that? I know it's kind of like gobbledygook, so hopefully everybody understands that. Okay. So the confidence interval estimates for the mean. On the left-hand side, if you can't see it, it says use Z distribution. If the population standard deviation is known or the sample is greater than 30, use the Z distribution. On the right side, we have using the t-distribution, If the population standard deviation is unknown and the sample is less than 30, we use the t-value. Okay, so these conditions must exist. The preference is to use the Z. When you don't have information and the sample size is smaller than 30, you use the t-distribution. So some of you may use a t-distribution for your case study. I'm not sure, but I think for most of you, if you're using the data from the website, they are all over a sample size of 30, so a Z-score you can use. So here's the rules. You assume the population is normal. Always assume the population is normal. Is the population standard deviation known? If no, use the t-distribution. If yes, use the Z-distribution. Is there any questions about that? Okay, so let's gonna look at the video for the confidence interval estimates for the mean. So remember, please ask questions if you're not clear on something. Okay.
Hello, this is Jeremy with Math Boot Camps, and in this video I'm going to go through 2 examples of how to calculate and find a confidence interval for the mean, assuming you're doing everything by hand. Now, of course, it would be advisable to use some type of statistical software, but going through the examples by hand is usually helpful in understanding what's going on. And sometimes if you're taking a course, maybe it's the only way you can do it. So when I look at these problems, I'm looking for 2 things. I'm either going to be working with a z-interval or a t-interval. And which one I use depends completely on 2 properties, mainly 2 properties. The big thing I'm looking for is if I know sigma or not. So if I know sigma, and that's the population standard deviation, then I can go ahead and use a z-interval. If I don't know sigma, then I'm probably going to be using a t-interval. Now there's a couple other things I mentioned too that are going on with this. Technically with the z-interval, once I know sigma, either I need a big enough sample size or I need a normal population. And the same thing's going on here. You're going to either need a big enough sample size or a normal population. What this is coming from, along with this property, by the way, what this is coming from is from the central limit theorem. So anytime I approach these problems, I take a look at them and I say, okay, am I estimating the mean? And then I decide, am I going to use a z-interval or a t-interval? And of course, there's very special cases where you can't use either, but we don't really go into those if you're taking an introductory course. Okay, so looking at this particular problem, it says we have a sample of 50. Okay, that's a big group. And the mean credit card debt for this group was $346. We have reason to believe that the population standard deviation, okay, that's pretty big. The population standard deviation is 108. Use this information to calculate a 95% confidence interval, et cetera, et cetera. So the important information I have here, I have a large sample size. I know sigma. And once I have these 2 properties, since we're estimating the mean, that's it. This is a z-interval. Okay, so the formula for a z-interval is the sample mean plus or minus a critical value times standard deviation over the square root of n. Okay, so this critical value, this comes from a table. The common values depend on the confidence level. And so for 95%, ZC is 1.96. Now, what is this really talking about? If you look under the normal distribution, it's saying that between a z-score of 1.96 and a z-score of minus 1.96, you have exactly 95% of the data. And so we can say that 95% of the time, a sample mean will be between these 2 values if we had the population mean in the middle. And that's where this confidence interval comes from. But for your sake, when you're just calculating these, you only really need to grab this value off of a table. So there's different for 90% and 99%, et cetera. Okay, so my X bar in this particular example is 346. I'm adding and subtracting 1.96 times, and okay, the population standard deviation was 108, and then divided by the square root of 50. So this entire right-hand side is called the margin of error. And so I'm going to calculate that first. and I get 29.9. So in some cases, what you'll do is you'll actually label this as your confidence interval. You'll put $signs here because this is supposed to represent debt, and that'll be your final answer. There is another way to write out.
Okay, just want to make sure, does everybody understand? You've got this mean, you've got the plus minus because that's what your z-score is going to be, plus and minus, because you're taking both sides from the mean. And what was I going to say? Okay, and that's your confidence interval. Okay, so you see that it's already in the formula. You've already created the confidence interval there.
This interval, and it's to actually do these operations. So I'll get 2 endpoints. And so the other way I could write this is I take 346 minus 29.9 and 346 plus 29.9, and I'll end up with 2 values that are essentially the endpoints of my confidence interval. So when I add it, I get 375.9, and when I subtract it, I get 316.10 or 316.1. So I could also write this confidence interval, and these are exactly the same thing.
Okay, and just sorry to add, the 1.96 and the minus 1.96 are the 95% confidence intervals from the right side and the left side. Okay, so they're equivalent. Okay.
As 316.1 up to 375.9. And so a lot of times in textbooks and calculators, they'll come out this way. And a lot of times in reports and things like that in the news, they'll come out this way, and they might not even mention a confidence level with those. So remember what you're saying with these is you're saying you're 95% confident that the true mean credit card debt for all college students in Illinois is somewhere between these two values, between $316 about and $376. So you're no longer talking about the sample, you're talking about the population, and there's a lot of other things to consider when interpreting these. So that's something you really want to study. I'm focusing on the.
Okay, so as I mentioned in the last class, and I'm going to look for it in your test and the exam and the case study, is remember there's a question being asked here, okay? Because the question in this case is use the information to calculate a 95% confidence interval for the mean credit card debt of all college students in Illinois. So she has found the confidence interval 316.1 to 375.9. You're going to end the question. Sorry, you're going to end the question, and your statement is going to be the 95% confidence interval for the mean credit card debt of all college students in Illinois is between $316.10 up to $375.90. Okay. Is anybody not clear about that? Because that becomes the most important aspect when you are answering a question. Okay, you're using all this math to solve whatever, the mean, the median, the standard deviation, the z-score. You want to come up with an answer in sentence form. So I will be looking for that when you are answering questions. Okay, just to be clear.
Calculations here, but the interpretation is very important. So let's look at another one and see how it goes. All right, so in this example, we have a sample of 38 employees. Okay, that's a big enough sample. They were surveyed and asked how many hours a week they thought the company wasted on unnecessary meetings. Okay, so the mean was 12.4, standard deviation was 5.1, and we're calculating a 99% confidence interval to estimate the mean. All right, we're doing a confidence interval for the mean. I know it's going to be Z or T. The question is, do I have a big sample? Yes. Next question is, do I know the population standard deviation? And some people may say, well, isn't that it right there? And that would be incorrect because this actually comes from the sample. If you look, it says the mean number of these employees. Who are these employees? The 38 we were talking about. That's a sample standard deviation. So while we have a big sample size, so n equals 38, we actually have a sample standard deviation of 5.1, and so sigma is unknown. We don't know the population standard deviation. So that means we use a t-interval. And so the formula for a t-interval is very, very similar.
Okay, so again, it's really important that you read the question carefully and you pinpoint, the mean number of hours these employees stated was 12.4 with a standard deviation of 5.1. Okay? These employees are going back to the 38 employees. This is not the population standard deviation. This is the sample populate standard deviation. Excuse me, sorry. So the important part is read the question carefully.
Take X bar, add and subtract a margin of error, but this margin of error comes from the t-distribution. So TC is kind of like that ZC we had before, and then S over the square root of N. Again, notice it's S instead of sigma because sigma is unknown. Now TC is a little bit different than ZC. We won't just have one standard normal or one standard t-distribution. With normal, Z is coming from the standard normal distribution. It's one particular normal curve. With T, it depends on the sample size. So TC could be a little bit different depending on if you have a large sample or a small sample. And any sample above 30, you could have a lot of different values. So the way we determine which one we're looking at is something called degrees of freedom. And that's n-1 in this particular case. So in this case, this example at least, degrees of freedom would be 38 minus 1, which is 37. Okay, I'm going to look on the table now. What I'm looking for is degrees of freedom 37 and a confidence level of 99%. And so many tables are situated slightly differently. Some may actually skip values and stop at 30 and start skipping. So you'll use the closest one if you're in that situation. But this particular table does have 37 in it. And I see that TC would equal 2.715. Okay, so I got that here in my formula written down now.
Sorry, I just want to go back.
Would equal to.
And I want to show you this table. You don't have to really worry about this. You'll see here a level of significance for one-tailed test and a level of significance for a two-tailed test. Okay? Can anybody think of what does that mean? What is a one-tailed test and what is a two-tailed test? Now, in her example, she's using a two-tailed test. And if you look at the graphs up at the top of this screen, you can sort of see what the two-tailed test is and what the one-tailed test is. So can somebody explain it in English? Well, I guess I'll have to ask somebody. Brenda, can you see what the difference is between a one-tailed test and a two-tailed test? Brenda, are you there? You're not sure. Okay, well, just take a guess. Just take a guess. Look at the graphs. And it's a one-tailed test, and what's a two-tailed test? Well, what are the tails? What do the tails represent? When you're looking at the graph, what are the tails?
I would say one-tailed test is for the specific group in one direction, but for two-tailed test, it's gotta be like negative or positive result at the end.
Okay. I assume that's not Brenda. Who is that?
This is Amir.
Okay. You're correct, Amir. Brenda, do you see that? In a two-tailed test, what you're doing is you're looking at both tails, okay? Over here on the right side and the left side. Okay. In a one-tailed test, now this gets a little complicated. You, as the researcher, is saying, I know where it's going to be significant, okay? It's going to be on the right-hand side or it's going to be on the left-hand side. most people that do a t-test and do a one-tailed test do not say those things. They usually do a two-tailed test because they are not sure themselves. Unless you've done something 1,000 times and you know it always comes out the same way, you as the experimenter are not going to say it's the right tail or it's the left tail. Okay? Is that clear? Does anybody not understand that? Because it's a really important thing that you may come across in the future. We're not doing it in this class, but it's good to understand this. Okay? So everybody gets that. All right, good. So
0.715. Okay, so I got that here in my formula written down now, or ready to be in the formula. So now I'm going to start plugging numbers in. So, okay, so the sample mean was 12.4. So I'm going to add and subtract 2.715 times S, which is 5.1, divided by the square root of 38. Okay, so first thing I'm going to do is calculate the margin of error. So that's at 2.715 times the 5.1, etc. Now I get a margin of error of 2.2. So we got 12.4 plus or minus 2.2. So this is one way we could list the confidence interval. But again, the other way is to actually calculate these out. So I say, okay, what's 12.4 minus 2.2, and what's 12.4 plus 2.2? So of course here, I'm going to get 10.2, and down here I'm going to get 14.6. And so I end up with the interval 10.2 up to 14.6. And so both methods or both versions that I've squared are the correct answer. It just depends on which way you would like to present it. And so again, what I'm saying here is that I'm 99% confident that the true mean amount of time that these employees think, all the employees at the company think is wasted on time in meetings is between 10.2 and 14.6 hours a week. So remember, that doesn't refer back to the 38 employees. It's talking about the population. And when we say 99% confident, what we're saying is 99% of the time this procedure will work. It will come up with an interval that's good, that we're telling the truth. The other 1% of the time it won't work. We'll think we're telling the truth, but we're not. And we don't know which group we're in because we don't know what the true population mean is. But for a procedure that works 99% of the time, we can be pretty confident. And that's where that phrase comes from.
okay, so one very important thing is what she said at the end. You don't know, in this case, what the population, you don't know what the standard deviation is of your sample, okay? So you're going to use the t-distribution to figure out your confidence intervals. You do it at 99% because your confidence in running the test is at 99%. 99% of the time this will occur. You'll have between 10.2 and 14.6 hours of whatever wasted on unnecessary meetings. Okay, but there will be a 1% chance that it'll be outside that range, either below or above. Okay, is there any questions about that? So everybody, you understand the difference between using the Z and then using the t-distribution to figure out your confidence intervals. Yes? Okay, great. All right, so we'll go back to the slides. Okay, continuing with when to use the Z distribution or the t distribution. If you look over here, now, I've been emphasizing you usually do tests at 95 and 99. Can someone tell me when you think you would use a 90% confidence interval? Well, we talked about it on Tuesday. Does anybody remember? No? The vaccine, right song, exactly. The pharmaceutical company will probably, I don't work for them, I don't know, they will probably never go above maybe 95. And maybe it'll always be between 90 and 95 because they're not interested in getting sued by people where the vaccine doesn't work. Okay, so when you use the 90, it's usually referred to, has anybody not heard of this term, a pilot study? Everybody's heard the term pilot study? Basically, it's an exploratory study. It's exploratory, okay? It's like I'm studying something for the first time. So I have no idea what's going to happen. So you want to set your confidence level around 90%, because if you get it within the 90%, then there may be something to the study. If it's below 90%, you can go, you know what, I got to rethink this and I have to redo it. So you don't waste that much time, or in case you're getting paid, you don't waste that much money. The 95% is at 1.96. Okay, and the 95 is the one that's usually used by most experiments. Okay, and the 99 is usually used when whatever you're studying has been done, you know, hundreds of times, thousands of times, so you can go higher than 95% because you're not interested in repeating what somebody else has done. You might be trying to find something else within that sphere, and so you want to go up to 99%. And these are the standard deviations, okay? All right, so this is the same example that we just saw in the video, so we don't have to go over that again. Okay, however, we'll just go over this quickly. So the plus minus indicates that you need to perform two different operations, subtraction and addition, because we're doing, as Amir pointed out, a two-tailed test, right? We're doing at one end and the other end of the curve. So we have the left hand, we have the right hand, and this gives us the 95% confidence interval from you, the population mean, as 316.1 to 375.9. That's your interval. Here's the important point. Well, it's part of the important point that I want everybody to try and do when you're answering questions, whether it's on the test, whether it's on the exam, whether it's in the case study. You say, we are 95% confident that the mean amount of credit card debt for all college students in Illinois is between $316.10 and $375.90. And please put in what the measurement is. This is money. You must use the dollar sign. You don't, this is where I'm going to be very hard in the marking. The units of measurement, in this case, it's money, you use a dollar sign. And I don't want one, in this case, 316.1 because the second decimal is 0. It's $316.10. Use the full number. So this is a very particular statement. So please make sure you study how to interpret confidence intervals in general so you can understand exactly what this means. Are you going to have time to do this? You should. Okay. I mean, it's writing a sentence, so it shouldn't be that long. Okay. And because you're limited and because there's a time limitation on the evaluations, I'm not going to ask that many questions like that. Okay. So the T intervals, The much more realistic scenario is using a t-interval to estimate an unknown population. This population mean. This interval relies on sample standard deviation in calculating the margin of error. And all this means is that the formula will be very similar, but the critical value will no longer come from the normal distribution. Instead, it will come from the student's t-distribution. It's called the student's t-distribution. I don't know what the history of that is. So, just to reiterate, when to use a t-interval, the rules are follows. The population standard deviation, is unknown and the original population normal, or the sample size is greater than or equal to 30 and population standard deviation is unknown. Sorry about that. I have to fix that. And the formula for the t-interval is the value of t depends on the sample size through the use of degrees of freedom, where degrees of freedom is defined as n minus 1. Your n is your number, your sample, and you subtract 1 from it. Any questions about that? Okay. So this is exactly the same thing that you saw in the video. Suppose that a sample 38 employees, blah, 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 were surveyed and asked how many hours they thought the company wasted on necessary meetings. The mean number of hours these employees, and look at the language, these employees, which means it's only from the sample, was 12.4 with a standard deviation of 5.1 in the sample. Calculate a 99% confidence interval to estimate the mean amount that at this company believe is wasted on necessary meetings. So as before, since you're estimating a mean with a confidence interval, you know it will either be a t-interval or a z-interval. In this case, you have a large sample, but you only have the sample standard deviation, not the population standard deviation. So if you aren't sure of that, you have to read closely. The standard deviation of 5.1 was in the context of the sample. So S equals 5.1, small s. Thus, you have to go ahead and use a t-interval since sigma is unknown. So before you can do that, you need to look up the critical values to know which row in the t-table to look at. And you find degrees of freedom, which is n minus 1 equals 38 minus 1 is 37. You use the table linked below here. Left-hand side, you've got your degrees of freedom. On the top, it's 0.01, which is 99%. Depending on what table you're looking at, either you look at 0.01 or you'll have a 99%, or you'll have both of them there. The t-table is not necessarily standardized by anybody who produces it, whether it's a publisher or whether it's on the net, or whether I can't remember what I gave to you, but they're equivalent there. And remember, you're always looking at the two-tailed, unless the question specifies that it's looking at one tail or the other tail. So now you have the numbers, you plug the values into the formula and do the calculations to get the two endpoints. The sample mean, 12.4, sample size 38. The sample standard deviation is 5.1. The t-value, 2.715. Right? In the chart here, 2.75, you got 37 degrees of freedom, 99%, that's your number. So you have 12.4 the mean, plus or minus 2.715, because it's two-tailed, that's why you're doing plus and minus. You get 5.1, 5.1 divided by the square root of 38. So the 99% confidence interval for mu is 10.2 and 14.6. Again, at the end, this is your interpretation. You are 99% confident that the mean amount of time that all employees at this company think is wasted on meetings is between 10.2 and 14.6. Any questions about that? I think it seems pretty straightforward. All right, we'll go to slide. Oh my God, sorry. Confidence interval for the mean. An example is using the t-distribution. Sorry, my PowerPoint seems to be all over the place here. Okay. So a tire manufacturer wishes to investigate the tread life of his tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inch of tread remaining with a standard deviation of 0.09 inches. Construct a 95% confidence interval for the population mean. And the question then becomes, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.30 inches? Okay, that's your sample mean. They're asking, is the population mean going to be that? So using the t-distribution, okay, see if I can make that bigger. And okay. So we have the mean 0.32 plus or minus, okay? We hear 0.9 is our standard deviation, the square root of 10. Okay, when we look at the table, we end up with 0.25 comma 9. Our t-score is 2.262 times 0.09 divided by the square root of 10. We look at the table on the right side. We have 9 degrees of freedom. We're looking at a 95% confidence interval. We have a number of 2.262. If you look on the graph, this is where 2.262 is on the right side. On the left side, it's over here. Okay? So you end up with, this is your confidence interval at 95%, 0.256 up to 0.384. The conclusion that you can come to is that the manufacturer can be reasonably sure, 95% confident, that the mean remaining tread depth is between 0.256 and 0.384, which is 0.30 inches is within this interval. All right, any questions about that? Everybody's clear about that? Okay, let me show you the video here.
This is Stephanie from statisticshowto.com, and in this video I'm going to show you when to use a z-score and when to use a t-score. There's a rule of thumb you can use. In order to use a z-score, which is preferable, you must know sigma, that's the population standard deviation.
Okay, she asked the question. It's preferable. Well, didn't she ask a question? I'm asking the question. Why is it preferable to use the z-score or the z-score? Can someone give me an answer? Why is it preferable? All right, I guess I'll have to ask somebody. Brissa. Okay. Why is it preferable to use the z-score instead of the t-score? Brissa? You can type your answer. You don't have to talk to the mic. You're not sure. Why not? What is it that you don't understand here? What is it that you know when you use a z-score? Do you remember, Brissa? What is it that you don't have when you use the t-score? Do you remember? Okay, can somebody help Brissa? What is it that you know when you use the z-score? What is it that you don't know when you use the t-score? Which standard deviation, Wellington? The standard deviation of the sample, the standard deviation of the standard deviation of the sample, or the standard deviation of the population? No, that's not correct, Wellington. When you know, okay, when you know the standard deviation of the population, you can use the z-score. And why is it preferable to use the z-score? Because it approximates it approximates the standard normal distribution, which is the population distribution, which is what you want, so it's closer to approximating the correct score. When you don't have the standard deviation of the population, it's sort of guessing. It's as close as possible. You're using the t distribution. So that's where the difference is. Okay? So I don't want to put anybody on the spot. I'm just asking questions and we're talking about that. Okay? All right.
And your sample size must be a 30 or above. Bear in mind, this is just a rule of thumb. If you want to use a z-score, then these two things apply. If your sample size is smaller than 30, you're going to use a t-score. And if you do not sigma, you would also need to use a t-score. Let me show you an example of how each of these work. Let's say you took the SAT and you scored 510 on math. You could.
Sorry, does anybody not know what the SAT is? You don't know? Okay. The SAT is the Scholastic Aptitude Test that they use in the United States. When people are in high school and they're applying to post-secondary school, they have to write this test and they have to submit it to the institution, or it's not submit, whatever institution they're applying to, they will get the scores. They will get their Scholastic Aptitude Test. And it's based on English and math and verbal reasoning or something like that. So we have to get the standard deviation less than 30 to use the z-score? No, you have to have a sample of 30 or more and have the standard deviation of the population, John. Okay?
You can look up the standard deviation and the means on the SAT website. And for 2013, we had a mean of 500 and a standard deviation sigma of 110. Our population is definitely more than 30. It's all the students that took the SAT. And we know sigma, so we can use a z-score. The z-score formula is z equals x. That's going to be your score, minus mu, all over sigma. Just going to plug those values in. X is 510, your score, minus 500, that's mu, the mean, all over sigma of 110. And if we calculate this out, we get 10 over 110, which is 0.09. So on a normal distribution curve, we have 0, which is the mean, and 1 standard deviation would be somewhere over here, but we have 0.09 standard deviations, so your score is going to fall roughly, very roughly in here. This is 0.09 standard deviations above the mean. So
Okay. Where is this person going to get into school? Can anybody figure that out based on these numbers? No one? No one wants to wager a guess, but you shouldn't be guessing. Let's just say an SAT, usually you need something over 700 if you want to go to an Ivy League school, which is like Harvard or Princeton or Yale. Okay, this person got 510. So where are they going to school? Yep, that's right, Song. They're just going to a regular everyday college. Okay, they're not going to get into, quote, an elite school. So this is what you've got to look at when you see the numbers. No, they might get into university, John. They might get into whatever. Okay, it depends on the regulations that the particular school uses. But a score of 510, okay, is not very high. So when you're looking at this data, that's what you have to interpret, that this person is, not necessarily going to get into MIT or Harvard, okay, or Oxford University, because their score is just not high enough. And now you know what their Z score is, 0.09, which is very, very low and very close to the mean. Okay, so I want you to look at that. That's the most important part of doing this.
for this example, we knew our standard deviation for the population, and we had a very big sample size. Let's take a look at a t-score when we don't have that information. Let's say you wanted to compare your GPA of 3.1 to other people. You may not have access to GPA records.
Okay, everybody know what GPA is? Grade point average. It's more, yeah, I don't know whether they didn't do it when I was in school, but that was in 1850. But do they still do GPAs now? Is that a big deal? Yeah, okay. I guess they had to adopt whatever the Americans are doing.
What's for the population you want to compare it to? So you do not know sigma, and you may only have a sample of, say, 25 students in your school. So we have a small sample size and we don't know sigma, so we're going to use a t-score. T-score formula is x minus x bar, that is the mean for the sample, all over S, which is the standard deviation for the sample. Again, we just plug our numbers in. My X, the number I'm interested in, is my GPA of 3.1. I'm going to subtract the mean. Let's say the mean for our sample was 3.2. And the standard deviation for the sample is 4.7. If we calculate this out, we get roughly negative 0.21. Now the t-distribution is similar to a z, it is symmetrical. And in this case, 0.21 would fall, see there's one there, 0.21 would be roughly here, slightly below 0. So we can use that t-score when we don't know sigma and when our population is small. So the rules of thumb, you can decide to use the z-score.
Okay, I'm going to ask another question. This is use your interpretation skills. Is a GPA of 3.1 good, bad, or average? Anybody? Vishani, why is it a good average? Why is that a good GPA, 3.1? From the formula that was done in the video, is this GPA 3.1 good or average or poor or excellent? Why did you say good? Can you tell me why? Do you have a reason why you said it was good? Roshani, are you there? How do you know it's above 80%? I'm not sure where you got that 80% from. Was that in the formula?
No, it's not in the formula.
But it's
Sorry?
pretty safe to use a t-score.
I'm sorry, what did you say? Roshani, what did you say?
It's not in a formula.
Okay, but I'm wondering where you got the 80% from.
So the 3.1 is it's equivalent to 80%, I think.
But where did you see that in the formula? I don't remember seeing that.
No, if we see in a percentage, I think 3.1. Okay, I think it's just my assumption. I'm not sure.
But if you look at what's on the screen,
Yeah.
the t-value is minus 0.21, so it's a little to the left of the mean. Okay,
Yeah.
80. That is not within 80%. That's not 80%. Okay, that's a little below the mean. Okay, for the t-value. Okay, you have to have a t-value that's probably 2.5 to 3, because you want it on the right side. That's where you're going to get 80%. So I'm not sure where you see the 80. Oh, are you subtracting 1 minus 0.21? Is that what you're doing? Is that how you got 80%? Is that what you were doing, Shani?
Oh, okay. I'm sorry. I
Okay,
think.
I just want you to be. I want you to be clear. The t-value is not the same as a z-value, and the t-value, similar to a z-value, is how close is that to the mean? And you can see minus 0.21 is very close to the mean. Okay, you're not subtracting 0.21 from 1 in this case. That's different. Okay, so I want that to be clear. Are you clear about that? Okay, so I just want everybody clear. The GPA in this particular case, using the t distribution, is pretty average. Nothing special about it. Okay?
But it's pretty safe to use a t-score if you do have that small sample and if you don't know sigma.
All right. I want everybody to be clear on this, the difference between the T and the Z. Okay? And you know what the criteria is. Okay. All right, we saw that one. And we did that one. And we did that. And we did this. Okay. So we're going to look at confidence intervals for proportion. And what is a proportion? It's a ratio. And what is a ratio? The same as a fraction. Okay, so it's a portion of the whole, and the whole always adds up to 1 or 100%. Okay, so a confidence interval for a proportion. So the examples below illustrate at the nominal scale of measurement. A career service director at Southern Technical Institute reports that 80% of his graduates enter the job market in a position related to their field of study. All right. Here's your proportion, 80%. That's where you're going to use a confidence interval. Example 2, a company representative claims that 45 Burger King sales are made at the drive-through window. Okay, here's the percentage. When you see the percentage, you know that we're talking about a proportion problem. The third example, a survey of homes in Chicago area indicated that 85% of the new construction had central air conditioning. And the fourth example, a recent survey of married men between the ages of 35 and 50 found that 63% felt that both partners should earn a living. Okay. And if we go back, you remember this, using the normal distribution to approximate the binomial distribution. You develop a confidence interval for a proportion, and you need to meet the following assumptions. The binomial conditions, as discussed in Chapter 6, have been met. Briefly, the conditions are: the sample data is the result of counts. Okay, you're just counting, right? Like in this 80% of the graduates enter the job market. There are only 2 possible outcomes. That's part of a binomial. Usually success and failure. Third, the probability of a success remains the same from one trial to the next. Okay, it's not dependent on what happened previously. And the trials are independent. This means that the outcome on one trial does not affect the outcome on another. Okay, so the values of n pi and n times 1 minus pi should both be greater than or equal to 5. This condition allows us to invoke the central limit theorem and employ the standard normal distribution, that is the Z, to complete a confidence interval. Okay, so and I've got a video with that.
We can also calculate confidence intervals to estimate population proportions. Now, first of all, remember point estimates. The value of any statistic that estimates the value of a parameter is called a point estimate. So what we're going to try to do is take a point estimate, the sample proportion, and create a confidence interval around it to estimate the parameter, which is the population.
Okay, so just to remind you, the statistic is used with samples, and the value of any statistic that estimates the value of a parameter, which is a population, is called a point estimate.
Population proportion. So here's my example. In a recent poll of 200 households, it was found that 152 households had at least one computer. Estimate the proportion of households in the population that have at least one computer. Now, our sample proportion is pretty easy to find. It's just x over n, or...
Okay, so if you recall doing proportions, we have the number that was found, 152, the total 200. To figure out the proportion, 152 divided by 200 equals 0.76.
Or 152 over 200, and we find 0.76. That means in our sample, 76% of the households have at least one computer. Now, this is just a single estimate. We took, one sample, entire population, just one sample. So it's probably off from the actual value of the population proportion that we're trying to estimate. Because of this, we're going to create a confidence interval to give a more realistic impression of what the actual population proportion value may be. So first of all, there are two requirements for constructing a meaningful confidence interval about the population proportion. And that is, first of all, the size of your sample has to be no more than 5% the size of the population it came from. And secondly, this weird equation right here, if the sample meets the requirement put forth in this equation, it means that it has approximately a normal distribution. So we can compare it to the normal Z distribution using Z tables and stuff like that. So first of all, back to this example, I want you to construct a 95% confidence interval to estimate the population proportion. Now, first of all, we have to check if it meets these two requirements. So the first one, yes, 200 households is definitely less than all of the households in the world, definitely 5%, less than 5% of all the households in the world. And second of all, our equation, we find that 36.48 is greater than 10. And don't get too caught up with the mean.
Okay, I just want to make sure, does everybody understand how he got those numbers? Does anybody not understand how those numbers were brought about? Everybody's good? Okay. Obviously, there's more than 200 households in the entire population of the world, as I said, and 200 households is less than 5%. Okay, that meets that criteria. And yes, if we multiply 200 times 0.76 times 1 minus 0.76 is greater than or equal to 10, that comes out to 36.48 is greater than or equal to 10. Okay, and remember, this is the complementary. You have to put that into the formula.
Of that, just realize that because it's greater than 10, it means we have approximately a normal distribution, and we can compare it to the normal distribution. So I'm going to take that away, and now we're going to use this equation to calculate the confidence interval. It's still just a point estimate plus or minus a certain margin of error. So here's our equation, and remember, we want to calculate a 95% confidence interval. That means we have the 95% in the middle and the 5% left over that's split into those two tails. Now, what's split into those two tails, the part that's left over, we're going to refer to as alpha. Alpha is the probability of making a type 1 error, but don't worry about that right now. Just realize that 5% is the part that's left over from our 95%, and it goes into the tails. So like in the equation, you see Z alpha divided by 2. Really, that's just saying, okay, Z 0.05 divided by 2. That means what is the Z score going to be when there is 0.025 in one of the tails? So then we have this table right here. We go to the Z table, and if there's 0.025 in the tails, that means there's 0.9750 in the body, and that means we're going to use the Z score of 1.96. Hopefully that didn't just confuse you. If I've already talked about this a few times, so I don't want to keep going over the same point, but if you look at the lecture on Z-scores, it might be a little bit more clear if you didn't understand this, where I got this 1.96 from. So we have this, and we're going to use the 1.96 for our Z. So now I'm just going to plug things into the equation. That should be a square root at the top, kind of got cut off. But you can see I put in the 0.76 for the sample proportion. I put in 200 for the size of our sample. And then I put in 1.96 for our Z. And I found what we refer to as the lower bound and the upper bound. So for our confidence interval, I am 95% confident that the proportion of households in the population with at least one computer is between 0.701 and 0.819. And that's how you construct a confidence interval around the population proportion.
Okay, any questions about that one? That was pretty straightforward. Any questions? All right, we'll go back to the PowerPoint. Sorry, I have to keep starting from the beginning. Okay, done that. And we just did that. Okay, so here's another example. The union representing the Bottle Blowers of America, BBA, is considering a proposal to merge with the Teamsters Union. According to the BBA union bylaws, at least 3/4 of the union membership must approve any merger. And what is 3/4 of the union membership in percentage? What does this mean? 3/4 of the union membership. What's that number? Come on, it's a percentage. It's a proportion. What is it? What's 3/4 of 1? 75, right, John? This is what you've got to do when you're reading the problems. So 3/4 of the union, at least 75% of the union membership must approve a merger. A random sample of 2,000 current BBA members reveals 1,600 plan to vote for the merger. What is the estimate of the population proportion? The question asks, develop a 95% confidence interval for the population proportion. Basing the decision on the sample information, can you conclude that the necessary proportion of BBA members favor the merger and why? So up here, you got to compute the sample proportion. You got 1,600 plan to vote out of the 2,000 is 80%. Now you're going to compute the 95% confidence interval using the Z-score because the sample is larger. So we can do that. The formula for the confidence interval. So we have a 0.80, that's our proportion, plus or minus 1.96, that's the 95% confidence interval, plus and minus. 0.8 times 1 minus 0.8 divided by 2,000 equals 0.8 plus or minus 0.018 equals 0.782 up to 0.818. And again, your interpretation, the merger proposal will likely pass because the interval estimate includes values greater than 75%, which is what it talked about. It said it needed at least 3/4 or 75%. This includes 75% when you're looking at the confidence interval, and therefore the merger will likely pass. Okay. Does anybody not see how the confidence intervals were created and what the conclusion was from doing this? Everybody's good. All right, that's great. Okay, the finite population correction factor. So the finite population correction factor, FPC, is used to adjust the standard error. We know what the standard error is. It means how much is left over, and you don't want over 10% of a sample mean when sampling is done without replacement. That means you're not putting back in numbers or whatever you're drawing, you're not taking them out from the sample. And the sample size is at least 5% of the population. The FPC factor always has a value of less than 1. In simple random sampling or sampling without replacement is a sampling technique wherein all the elements of the sample are randomly selected from a given population. Each element of the sample has an equal probability of being chosen. A simple random sample is an impartial representation of a group. Errors may occur if the sample does not reflect the population from which it was taken from. The standard error of the mean, also known as the standard deviation, refers to the measure of the margin of error of a sampling distribution. We've gone through this previously. In a relatively small finite population size, of which the value is known, the finite population correction factor can be used to estimate the standard error of the mean. This accounts for the increase in accuracy if a larger percentage of the population is randomly sampled. As we talked about before, increase the sample size, it approximates the normal population. Given a sample containing an n number of objects, which were randomly selected from a population size of large N, the finite population correction factor is calculated by taking the square root of the population n minus the sample n divided by the population n minus 1. Okay, now, after all that confusion or misunderstanding, this video should show you very quickly about the finite population correction factor.
In our previous videos, where we're talking about finding the confidence interval for our population mean, or even our proportion, we're talking about the sample size of n, and we're assuming that that sample size is small relative to the total population, or cap n. If instead that sample size of little n divided by our cap n is greater than our 0.05 mark, we're going to consider that a large percentage of our total population. And in that case, we're going to have to impose what's called a correction factor on our standard deviation for our sample means of x bar. And that correction factor is equal to the square root of our cap n minus our little n over our cap n. So to impose that correction factor, we just multiply that value by what our normal formula for our sample mean standard deviations. So we'll say S over square root of n. And that's our simple correction factor. We just multiply those two values together, and that gives us our updated version of our sigma sub x bar. And that same formula can be imposed for our sigma sub p hat, which would then come out to be, we have our square root of p hat times q hat all over n, and then that value multiplied by our correction factor, cap n minus little n over cap n, and the square root of that value as well. And that's just the method that we're going to use to impose a correction factor on our standard deviation for our sample means.
Okay, but remember, this is a criteria. Okay, although the PowerPoint, it does say 0.1. This one's a little more strict. If you've got a question about it, you certainly will accept 0.05 and above. Okay, just because I showed it in the video. Are there any questions about this correction factor? No questions, okay. Go back to the PowerPoint. Okay, so we'll just have an example here. So a population, the finite population correction factor, a population that has a fixed upper bound, like it has a max, we cannot go any higher, is said to be finite, obviously. So for a finite population where the total number of objects is large n, and the size of the sample is small n, the following adjustment is made to the standard errors of the sample means and the proportion. However, if the sample n divided by the population n is less than 0.05, the finite population corrector factor may be ignored. Okay? Because you want your error as small as possible. Why? You can see what happens to the value of the correction factor in the table below when the fraction sample n divided by population n becomes smaller. So this is the formula for the standard error of the mean, and this is the standard, sorry, this is the formula for standard error of the population. Okay? So the FPC approach is one when the sample n divided by the population n becomes smaller. So finite population correction factor for selected samples when the population is 1,000. So we have a sample size of 10. It's 10% of the population. That's the correction factor. As the sample size increases, if we have 500, that's 0.5 of the population. The correction factor is 0.7075. Okay. Any questions about that? No questions? Everybody still awake? Okay. So the confidence interval for a mean with the population correction factor. Example. There are 250 families in Scandia, Pennsylvania. A random sample of 40 of these families revealed the mean annual church contribution was $450, and the deviation of this was $75. Could the population mean be $445 or $425? And what is the population mean? What is the best estimate of the population mean? So look at the problem. This is what you're given. Okay. This is your large N, 250. That's the total population. Okay. The random sample of 40. So N is equal to 40, small n. Okay. And the standard deviation, S, is $75. This is all given. And I'm just going to mention something. When you have a problem, write down what's given, because obviously what you're going to have to find is what is not given. Okay? So, what can we do with these numbers? Since the sample divided by the population is 40 divided by 250 equals a 0.16, the finite population correction factor must be used. Why? Why must the population correction factor be used? Anybody? What's the criteria for using the population correction factor? What have we been saying? Remember, less than, yeah, right, okay, but that's also, it's 0.5, remember. Look at that number. So the population standard deviation is not known, therefore use the t-distribution, but you could use the z-distribution since n is greater than 30. Okay, so in the formula, we have 450 plus or minus, okay? Plug in the values. So we have 450 plus or minus $19.98 times the square root of 0.8434. That's substituting these numbers in. We have $450 plus or minus $18.35. So our confidence interval is between $431.65 up to a maximum of $468.35. So now you found this. Now you have to answer the question. So it is likely that the population mean is more than $431.65, but less than $468.35. To put it another way, could the population mean be $445, which is what one of the questions was? Yes, but it is not likely that it is $425 because you already have your confidence interval here between 431.65 and 468.35, because the value of 445 is within the confidence interval and 425 is not within the confidence interval. Okay, so are there questions about that? And remember, I want you to get used to answering the questions with, you know, a little paragraph or a couple of sentences at the end. Okay, you're figuring out what you have to figure out, and then you're going to plug it into a sentence or a paragraph or a couple of sentences. Okay? All right. Now, when you are doing a study, if you're going to do a study, if some of you are doing a case study and you want to pick an appropriate sample size, before you calculate a sample size, you need to determine a few things about the population. First, how many total people fit into the demographic that you're looking at if you're using people? You don't have to use people. You know, it can be anything. So for instance, you want to know about mothers living in Canada. Your population size would be the total number of mothers living in Canada. Not all population sizes need to be this large. Even if your population size is small, you just know who fits into your demographic. This is talking about doing surveys with people. So don't worry if you're unsure about this exact number, but you can apply this to anything. It is common for the population to be unknown or approximated between two educated guesses. Your margin of error, your confidence interval, no sample will be perfect, so you must decide how much error to allow. The confidence interval determines how much higher or lower than the population mean you are willing to let your sample mean fall. If you ever see a political poll in the news, you've seen a confidence interval. So, for example, it will look like 68% of the voters said yes to Proposition Z with a margin error of plus or minus 5%. That's your 95% confidence interval. We talked a little bit about this, okay? You don't want to go below 95%, and why is that? Can anyone tell me why you don't want to go below a 95% confidence interval? We talked about it. Noah? Why do we not want to go below a 95% confidence interval? You don't have to talk. That's not answering the question, Amir. I want you to talk. I want you to answer statistically. Noah, can you answer? Are you still there? Noah, you don't want to talk? Do you understand? Okay, so why do you not want to go below 95%? Oh, you're typing, sorry. Okay. And remember what I said, Amir. You've got to answer more completely. This is not an answer.
I would say if we apply that result in the large population, we're going to see more error. Like
that's what I want to hear.
If we assume if our sample is 10,000 and we have we have an error of 7%.
Right.
We're gonna get 700 people or anyone or whatever.
Yeah.
It will be wrong. So
it's not going to be wrong. It's going to you said it's not going to be accurate, which is what it is. And like Noah has said, once you get away from 95 or 99, usually 95, your error is going to increase. When your error increases, you're going to get false positives. When you get a false positive, then it's screwing up your data. Okay? That's what I want people to think. Okay? Think statistically, because you say the confidence interval is 90%. Well, that means it's a 10% standard error. If it's a 10% standard error, that is already increasing the error likelihood in your data, which means you're going to get false positives, you're going to get false negatives, and you, who is doing the research, is going to make a false assumption about your data. That's the most important aspect. Okay, so I want everybody to understand that, because you have to think statistically about, if you get a question and it says, yeah, okay, for example, in this one it says 68% of the voters said yes to Proposition Z with a margin of error of plus or minus 10%. Well, is that poll accurate? No. Okay, because you're already admitting that you have a standard error of 10%, which is what you do not want. You want it as close to zero as possible, so why are you increasing? Okay, I just want people to think statistically when they see the data. I know it's difficult because you don't have a lot of experience, but try to look at it that way. So let's just go through these two things here. Your confidence level, how confident do you want to be that actual mean falls within your confidence interval? The most common intervals are 90%, 95, and 99. I am saying when you see something that's 90% confident, I wouldn't be so confident about how accurate that whatever survey poll is. Okay, so you can look at it and go, yeah, okay, we got 10% error. That's a lot. Standard deviation, how much variance do you expect in your responses? Since you haven't actually administered the survey, the safe decision is to use 0.5. This is the most forgiving number and ensures that your sample will be large enough. Okay? You don't, you're measuring something and you don't want it to vary that much. Okay? Are there any questions about this? This is all preparation to selecting an appropriate sample size. We're not going to do that. We'll do that on Tuesday. But I want everybody to understand these are the conditions you have to have in order to select an appropriate sample size. So, are there any questions about this? Okay, there's no questions? All right. So, I'm just going to remind people the Chapter 7 test will be available as of 5 o'clock today, and you have until 5 o'clock Monday evening to complete it. And I sent a couple of notes to people regarding their case study. Get back to me. If you're not using the data set that's available on the website, I need to see the data set that you're going to use, because I want to know where it's coming from. I want to know if the data is valid and it's from a reliable source. Okay, so are there any final questions? No final questions? Okay. So everybody have a good weekend. Don't rush through the test. Think about the questions. There's 53 questions. Okay. So have a good weekend and wow, okay. That's a lot. Yeah, but you can do it. So have a good weekend, and I'll see everybody, or not see you, but hopefully we'll hear from you on Tuesday or before that, and office hours are on Monday from 10 to noon. Okay? Thank you.